Okay, hello everyone. I'm going to talk about the design of Uber, the system design problem about the designed ride-sharing system. I use the Uber as an example. The Uber is a ride-sharing platform that connects passengers with drivers who offer transportation service in personal vehicle. It allows users to book rides on demand from their smartphones, matching them with nearby drivers who take them from their location to their destination. Okay, let's start from the requirements. Start from the functional requirements. The riders requires estimate fare. The fare means money. Riders expect fares to get matched with the driver, and the driver can accept it or deny it, and then navigate to pick up or drop off. So out of the scope have some like rating riders, scheduling the drivers in advance, and supporting different ride types. This is the functional requirements and the out of scope of the functional requirements. Here has some non-functional requirements like low latency ride matching, smaller than 1 minute, and strong consistency for matching, and handle surge 100K from same location at the same time. So out of the scope, we have the those of things it will not in our current design solution here. So we have some very key point about core entities like driver, rider, fare, ride location. And for the API design here, we have the post for the matching for the first one, post to estimate the ride based on the pickup location and destination. And then this post ride is kind of like a current here. I already estimate something. The riders is okay. I accept it. I want to send to the driver. I want to match to the next steps. Then it's kind of like sending a request. Okay, I accept the money. I want to match the driver. So this is meaning about this API. And for here is post the driver's location. Is the drivers, right? There has so many cars, and they were sending their location to the backend server, and backend servers were based on their location to match for the riders. So this is the this post API meaning here. Okay, so for the patch is based on the rights, and the drivers can accept it or deny it, right? So it's kind of like this patch is matching for these functional requirements. So let's see what about the high level design. Let's start from the first red one. The riders require estimate fare, right? So this is rider. The rider can, based on their phone, like iOS system, Android system, to sending the requires to this one. This is the API gateway. It has some functions like load balance, routine, authentications, right, SSL terminations, rate limit, and then sending the requires. It has for the backend, it has the ride service to calculate the estimate fare, to handle the fare estimation. So we can get the fare estimate from here. And for this third-party mapping, it's kind of like we can integrate with like Google, because we have some destination. We need to use some third-party mapping to get the location. Then it has some information, then come back. Okay, so I know how the distance about this one, then calculate. And then this also has the database to store some information, like if current estimate ride ID is what, and how much about this, or whether destination and whether the status, whether rider is okay for this one, right? So this is kind of like and also have the rider about the meta data for here. So let's see, and this is for the first high-level design, and what is the rider accepted fare to get a match with the driver. So for here, rider accepted for fetching the driver. We have the ride matching service to have some logic to match the driver and the riders, right? Get the status. And also we have the database, right? So we rider match service need based on the driver's location. So for the driver's location is here, like driver, right? It has some location updates. It will sending a current location to the backends, which is called the location service, and update their location and also store in the database. And then for the rider service, matching service, it will get some relative location, right? To get how many drivers are around the destination, how many drivers are close to the rider's pickup location. So this is how it's work like here. And then match, and if they are matched okay, then it will return back for the rider, and also it will have some update for the rider for the status update. Come here is matching or is finished, and also match for the driver ID. And the third third functional requirement is driver can accept, deny, and navigate to pick up and drop off. This is kind of like a notification, right? When the driver's here, it will get some information here. Oh, current here, you match for which ride. Then you can. This is APM, means Apple notification. This means the cloud notification sending back to the driver, and the driver can say, "Oh, I accept it or deny it," and sending to the backends, and they will update the rider informations current here on whether current ride whether is okay, is denied, or you have to rematch. So this is the basic functional requirements. And let's go into the deep dives. Non-functional requirements. Let's start from the first one, low latency. So suppose we have the 6 million drivers and 3 million active drivers, right? So this is the transactions per second. And for this so many things, we need to use like a Redis, right? Redis for the database, searching so many drivers, we need a good way to search from the database. So we can use the Redis to solve this problem. And the Redis also can, based on the geohashing. What is geohashing? Geohashing is here, right? You have this is like the whole world map. And for here, we separate like four parts. And for 2 here, we also can separate it into the 2 parts. Just to make sure how many layers you want, it can exactly what you need. So you just keep separated. So for the good way about this is simple represent as the single string, and mark it easy to store and share. Efficiency for proximity search, as nearby location often share a prefix and the uniform distribute of hashing value. And also it has some not good part is precise varies across the latitudes. Higher latitudes have less precise, not as effective for bounding box searching due to its z-order curve property. Boundary issue is adjacent areas may not share the same prefix, completing proximity search. Okay, so the search is, I think it's somewhere like, it's like this boundary, right? For the boundary, how could you identify that? So this will need to a better design for that. So it's a very challenge is for here, boundary design here. Yep. So let's see. So we can use this way to improve the low latency. And the second is strong consistent for matching. So for the consistent matchings, we have two problems. We don't send more than one requires a time for a given write, right? So there has the writer want to send in the write. It was sending just only for one driver, one possible driver at a time. Not send all of them, because if they send all of them and there are 10 drivers pick up the requests at the same time, that's maybe encounter some problems. So we can use this, which is the driver log, to make sure current driver whether accepted. If the driver accepted, this request belong to current driver. If not, like if it 10 seconds, if not, if the driver not respond, it will move to the next one. And the second one, we don't send any driver more than one request at a time, right? So we have to add some sending. We don't send any drivers more than one request. Yeah, the driver we have pick up here, like you can write some logic inside the matching service. There are so many drivers, right? So you can just focus on one at one time and get the response and send it to the next one. And what is handle surges 100K from the same location at the same times? At this time, we can add the request queue, just the one by one to solve the problems. It will be great way to, like Kafka, to handle this problem. Yeah, this is the deep dives example here. And thank you.